This video is part of a course on food physics. We are in microwave heating, which is in two parts, and this is part 1 dealing with electromagnetics. This part is in 6 section, and this is the section 3 of that. In this section, that is part 1.3, we're talking about dielectric properties and energy absorption in food. As I said, this is the section 3 of the 6 section segment, that is part 1, talking about the electromagnetics. So in this section, we are talking about how the properties of food material affect energy absorption. So the section before, we talked about how energy propagation occurs in a simple geometry like a slab, and the section after, which are separate videos before and after, we talked about how electromagnetic waves behave inside an oven. As discussed earlier in the series, water molecules and ions in food try to align with the field that keeps changing directions. Since it's a wave, so that's the microwaves that are changing directions. The electric field is changing directions, making the water molecules and the ions move. That's how it generates heat. Although we use one, maybe two frequencies in practice for generating microwaves, it is useful to get a general picture of how this interaction of, let's say, the water molecule or the ions would vary with frequency. Now we have two properties that determine how the material would behave in an electric field. Those two properties are dielectric constant and dielectric loss. So let's start with the dielectric loss, for example, and that measures the ability to dissipate energy or to produce heat. So it measures the ability to generate the heat. Now it is the movement as shown like these that you're seeing. It is the movement that generates the heat. So at a very low frequency at this end here, at this end, then this water molecule is going to rotate ever so slowly. So of course it's going to generate less heat. So then the property that determines the ability to generate heat, dielectric loss, is going to be small in this low frequency range. At the opposite extreme, at the high frequency range, when the field changes directions too fast, then this molecule, we can kind of think of it as like an inertia. It's not going to be able to follow the field. So again, the dielectric loss, or the property that measures the heat dissipation, changing of electromagnetic energy to thermal energy, is going to be small because the molecule is not even able to really follow the field and thereby generate the heat. In between, when it's able to follow the change of field and it's fast enough, it's going to have the maximum amount of heat generation. So the typical symbol used for dielectric loss is epsilon double prime. So epsilon double prime is going to vary with frequency this way. This is a very general kind of a concept. We only need values at like one frequency. Okay. Um, the other property, dielectric constant, which by the way is represented by this epsilon prime, it measures the ability to store energy. So at the low frequency range, it's able to follow the field and thereby store energy. So this property has the highest value at this low frequency range. At the higher frequency range, it is not even able to follow the field. So forget about storing energy. So it's not able to store any energy. So the property that kind of represents that ability or the measures the ability to store energy is going to approach zero. So the variation is going to be something like this. So this is the big picture of variation with frequency, and it is these two properties of the food that will provide how it will heat in the microwaves. But this is not the only these properties are not the only thing that decides how a food will heat. There are other factors. That's why we have other sections, other videos in this series. Now we relate the properties we saw to heat generation. So here Q is the heat generation, let's say in watts per meter cube, and that is equal to 2 pi f, where f is the frequency of the microwaves we're talking about. Epsilon 0 is an universal constant permittivity of free space, and epsilon double prime is the dielectric loss that we just talked about, and then multiplied by the electric field at that location, the magnitude of the electric field at that location squared, so electric field intensity. Now this might make somebody think, okay, so all I need to know is this dielectric loss to determine how much is heating going on. What is the constant doing? What is not obvious from this formula is the food inside the electric field inside the food depends on the dielectric constant. A formula, not valid universally, just from static electricity, the electric field inside the food is electric field inside the oven, that's in the air, divided by dielectric constant. This is not an universal formula. It's just showing qualitatively that the food inside is the electric field inside food is related to electric field inside oven by the dielectric constant. So the point being made here is heating depends on both properties, not just dielectric loss. So it depends on both epsilon double prime dielectric loss and epsilon prime the constant. So this is the loss, also right, the fully called loss factor, and then this is the dielectric constant. Okay. We now want to get a feel for these properties a little more. So first, at a surface, when a electromagnetic wave hits, okay, a surface, so this could be surface of food, let's say, and so this is food, and let's say this is air, okay. So this is the surface of the food. As the electromagnetic wave hits, it is the property of waves, any wave, when they hit different medium whose properties are different, part of it is reflected and part of it is transmitted. And so in case of this air and food, when microwaves hit the surface, part of it would be reflected and part of it is going to be transmitted into the food. So if we think of the electric field hitting the surface, if we think of the normal component this way, then for simple situations, very simple situations, we can relate the normal component outside and the normal component inside by this kind of a formula where the electric field inside and electric field outside are related to the dielectric constant that we just discussed. So what this means is going to look something like E food over E air is going to be so for air, dielectric constant is 1, and then for food it's, let's say, epsilon prime. So as I talked earlier, inside the food it's going to be lower. Inside the food, E food is going to be E air over epsilon. This is not to be generalized, this formula. This is just a sort of almost a qualitative picture of what's going on at the surface. Pictorially, so inside the food, then here inside the food, the electric field is going to be related to the electric field in the oven that's in the air. This is my E oven. And so in the food at the surface, just at the surface, but inside the food can be something like this. Again, not an universal formula, but gives us the qualitative picture. Now, inside the food, as the wave travels, its energy is deposited, and that's how it heats inside. Now, how does the electric field change inside the food? It's generally quite complex, but just qualitatively, for qualitative discussion, we want to use the formula or the derivation and understanding that we developed for plane waves hitting a very thick region. So not for the oven. So the formula you're seeing is not for the oven, but for that semi-infinite region or very thick region. So for that, the electric field magnitude decays this way. Electric field magnitude decays this way as it enters the food, and from that exponential decay of electric field, we can write the heat generation term this way. So first of all, let's look at this part, the numbers in the front. And so we see that the heat generation, it depends on its value at the surface. So from the surface, it decays. The heat generation decays. So this is my Q decaying. And the value at the surface depends on the loss, and it also depends on the electric field in the food but at the surface. And we know from a previous discussion that the electric field at the surface inside the food is going to depend on the dielectric constant. So both of these show that the heat generation at the surface is going to be depending on the dielectric constant and dielectric loss of the food. Now how it penetrates the material is given by this. So how it changes with position inside the food. And here you see we have this alpha. So this alpha actually depends on both the constant and the loss. If you recall, in the past we have also written it this way: Q is equal to Q0 e raised to minus x over delta, where delta is the penetration depth. Okay, and this delta is nothing but 1 over 2 alpha. So just like penetration depth, as we'll show in more details later, penetration depth depends on dielectric constant and the dielectric loss. So does alpha, and therefore the decay, how it decays in there, is also going to depend on the dielectric constant and dielectric loss. So both the value at the surface and how it decays is going to be determined by these properties, the two properties. So these two properties that we just discussed, that capture all the interactions, not just the dipolar and ionic that we are showing, but if there's any other interactions, they capture all of those. How do those properties vary for different foods? It would be nice to have a big picture of that, and that's what we see here. It shows a pair of dielectric constant and dielectric loss for a whole bunch of foods, and it shows a fairly big range. And the frozen material, for example, ice does not interact with microwave. So frozen materials have the lowest value, but also low moisture foods, they have some of the lowest values. And then if you increase water content, then both the dielectric constant and dielectric loss factor increases, and they increase because there's more and more water, more and more components that are microwave active. It is important to know that while this picture gives us some idea how, let's say, a frozen material would heat versus a unfrozen material, let's say frozen meat versus unfrozen meat would heat, it only gives a partial picture. It does not give a comprehensive picture. Just knowing these properties, it does not give a comprehensive picture of how a material will heat, unfortunately. Why? Because the details of heating depends on the size, shape of the food, also some oven factors, and even other properties like thermal properties such as specific heat. So we're going to see that in the next slide. At this point, the dielectric properties alone are not enough to decide how the food will heat. This would be illustrated using a case of thawing. So here we start from frozen or frozen foods that have very low value of dielectric constant and dielectric loss. And so if we have this scale of dielectric constant and dielectric loss, we are starting off somewhere very low value. So initially the constant and loss, they're both blue, meaning very low value, frozen. And then as we start to thaw, as we heat, so these, by the way, are cubes of material with properties of meat, and what I'm about to show are from computer simulations that did the full electromagnetic study of the oven plus the frozen food as it's being heated. So it is not from plain electromagnetics, it's from oven heating. So what I am showing you, the constant and the loss, these are from that cube. It's one section, so it's a square. It's one section of the cube, so it's a square. It shows the value of constant and loss, which are very low to get started. And then when it thaws, it looks something like this. So when it's part thawed, not totally thawed. So again, the top one is dielectric constant and the bottom one is dielectric loss. So as the material thaws, it moves this way. This is frozen meat, so it moves this way, right? It's not going to move linearly, but it's moving in that direction. And as it thaws, it happens to thaw on the surface. So on the surface, we get these values of unfrozen, which are much higher. So you can see the values are here on the surface. So the thawed material, that is water instead of ice, much higher values of dielectric loss and dielectric constant. But let's think of the dielectric loss for a moment. And so it should be a lot more microwave absorbing, right, compared to the frozen material. Is that true? What do you think? It turns out no. The total amount of energy or the power absorbed over the entire volume is much higher when it's frozen than when it's partially thawed. So the values of power absorbed goes down from here to here. Why? Because when it was frozen, its properties were closer to that of air. So there was less mismatch between air and the frozen material here. So we're talking these two here. It's less mismatch. So then the more energy from the oven could actually get into the frozen material because there's less mismatch, not as much reflection from the surface. So opposite is true when it's thawed. So when it's here, properties are much different from air. Air has the property of 0 loss and 1 as dielectric constant. And so it's now much different from air. So when the waves are incident on the surface, a lot more would be reflected, and so there is a lot more of the mismatch, and because of this mismatch, more energy would be reflected, and there's just going to be less coupling of the energy, so less energy will get in. So we'll actually see a much lower overall power absorption in the material. So this is just to make the point that it's complicated. It's not just properties. There are other factors that we will talk about in other videos, but it's not like we can just look at the properties and say, that's how it is going to heat. Thinking of the solution that we had earlier, Q equal to Q0 times e raised to minus x over delta that says that heat generation decays exponentially into the material. This is not for oven heating, it's for plain waves in a thick medium, but like before, we want to get some qualitative understanding using this simple formula. Even some of it would still be applicable to the oven heating. So we look at this delta as the penetration depth, and that penetration depth is defined in terms of food properties this way. And by the way, the meaning of the penetration depth again is the distance delta over which the power, the heat generation rate falls to 0.37 of its original value. So that's the physical meaning of the penetration depth. So lower the penetration depth, that means energy does not penetrate very far. Lower penetration depth would happen when the material is very absorbing. So let's see this formula for penetration depth. Does it make sense? So you notice that epsilon double prime has to do with the absorption. So if the absorption is very low, let's say it's 0. If absorption is 0, then the wave should just keep going. It should not decay at all. And so it should have very large penetration depth. And let's see if we actually see that. So if we put this epsilon double prime equal to 0, then we get square root of 1, which is 1. 1 minus 0 is 0, and that raised to the power minus half gives me delta going to infinity, which is what we should get, because if it is not absorbing, then it's not decaying at all. So penetration depth would be infinite. So on the other hand, if we have a very large value, let's say of epsilon double prime, then penetration depth would be small. So that dielectric properties, those properties that I showed earlier, if I use those values to calculate penetration depth for different situations, this is how it looks. So for very low values of dielectric constant and loss, for frozen foods, for example, the penetration depths are much longer. Whereas meat juices or something like a soup that has lots of water and lots of ions, then the penetration depth is going to be much smaller. You notice this is like 0.5 centimeter or half a centimeter or 5 millimeters. So this, for example, shows up in when we are heating a large bowl of soup, and the outside heats a lot more, whereas the inside could stay cold. That's an example of the sort of manifestation of this penetration depth. So this again is a useful piece of information to try to understand how something will heat in microwaves. Here we want to look at how temperature affects dielectric properties. Now it's hard to talk about the temperature effect for a complex system as food is. So these plots are for a simple system that could get closer to or somehow can represent at least partly how foods would behave. So these are for distilled water and solutions of water with salt in it. So first, the dielectric constant. So the dielectric constant, as the temperature increases, dielectric constant decreases with temperature. If we look at dielectric loss, again, let's stick to distilled water first. So for distilled water, then as I increase temperature, the dielectric loss also decreases. It decreases because movement due to the applied field is reduced. When salt is added or the ions are added, then the dielectric loss would be a combined effect of this dipolar effect plus the ionic effect. Whereas the dipolar effect decreases with temperature, the ionic effect increases due to increased mobility of the ions and the decreased viscosity of the liquid. The total loss, which is what you are seeing here, this is the total effect of the dipolar and the ionic, that changes in a way depending on which one of those two effects dominate. At higher salt contents, the ionic effect dominates, and that increases with temperature. The ionic mobility increases with temperature, so the total dielectric loss increases with temperature. With higher salt content, as we increase the salt content, dielectric constant goes down, because after all, salt is replacing that of water, and therefore the more microwave active component is being reduced. More drastic effects of temperature can be seen during phase change. For example, going from frozen food to a thawed food. So here we see the property change. In this case, it is estimated based on the frozen fraction. It is for a food analog, that is tylose, with the properties close to that of beef. In this range of phase change, as the material thaws, going from ice to water, ice absorbs very little microwaves, and water is very microwave absorbing. So you can see tremendous increase in both dielectric constant and dielectric loss as it approaches a thawed state. Now this has major implication in a thawing process, as already discussed a few slides ago in this video, but there is also other videos where we talk details about a thawing process and how this huge change in properties, both dielectric constant and dielectric loss, creates many interesting aspects in heating frozen foods. Now, after the material thaws, then its behavior is kind of more along the lines of what we just discussed. So you see the dielectric loss increases with temperature. Dielectric loss increases with temperature because after all it has salt and ions, and we just talked about that. And then dielectric constant decreases with temperature, just like the way we discussed in the previous slide. Like temperature effect, there's going to be composition effect, obviously, right? Less moisture, meaning the dielectric constant and dielectric loss, they will both get reduced. So here is an interesting example where we're showing how the properties change during a drying process as we reduce the moisture. these properties are not directly calculated but estimated based on how during drying the moisture phase changes. So we estimate based on properties of the solid and in the amount of water that is in there. Such estimation process uses standard formulas in the microwave literature for calculating properties of a composite material. So it's reasonably a valid way to estimate these properties, which are nearly impossible to get this kind of detailed data. Okay, so this is for potatoes. This is for potatoes, and as you expect, as the moisture goes down, the properties, both dielectric constant and then dielectric loss, they go down. So here it's this one and this one, let's say. Okay, so let's look at the black set of lines first, and then we'll look at the other set of lines. So they go down because as moisture content reduces, it just reduces the dielectric property. There is less microwave active component there. Water is getting replaced by vapor and air, which have much lower dielectric properties. But the black lines were obtained considering no shrinkage of the material, which is of course not realistic. So when we include shrinkage, which are the red set of lines, inclusion of shrinkage, then the property drop is not nearly as drastic, and it makes sense because now we don't have these large pockets of air being developed because the material shrinks, so it kind of takes over some of the space that water was there earlier, so that the shrunk material, which is the more realistic one, the material property, the dielectric constant, dielectric loss, they don't drop as quickly. So a side note, in a process such as microwave drying, if we are trying to estimate, let's say, drying time and so on, the properties that we will use, we have to be very careful how to estimate them. This effect is real. As it shrinks, it kind of takes over the space that would have been for air, and thereby reducing dielectric property. So it doesn't reduce as much. Summarizing this really long video on dielectric properties, let's make a few points quickly. So the primary interaction of microwaves are with the water molecule and the ionic components. They are by no means the only components that interact with microwave. For example, even oil heats, and oil does not have the water or the ions. So there are other mechanisms, but these two, water and ionic components, are the primary components that are able to interact with microwaves and generate heat. So their ability to interact with microwave are characterized using two properties, dielectric constant and dielectric loss. Together they decide heating, not just one item, just the dielectric loss, not just one property, but together they decide heating. But even together, they are not the only determining factor. These properties are not the only determining factor of how a material would heat in the microwave oven. Um, the properties of food cover a wide range from very low value to very high values. And finally, there's temperature effects and moisture effects on the dielectric properties. So with temperature, the properties can change, and especially when there is phase change, the change can be significant. Likewise, with moisture, the properties change significantly. Reducing, as you reduce the moisture, the dielectric properties, both constant and loss, they go down. So again, these properties alone do not determine the rate of heating inside a microwave oven. We also need to know the shape, size, oven details, like whether there is rotation of the food and so on. So later we have two videos, one talking about food factors in addition to dielectric properties in microwave absorption, and then another video on oven factors in microwave absorption. But the very next video would be, what does it look like inside an oven? How does the microwave field look like inside the oven that will do the heating?